Okay, so I guess it's time to go ahead and get started. So before I introduce our speaker, I want to remind everyone that you can ask questions if you're watching on Zoom via the Q&A box on the Zoom webinar, or if you're watching on YouTube, you can enter your questions for Ania in the chat on the right-hand side next to the video. And after the seminar is over, there will be a post-seminar discussion with the speaker. Everyone is welcome, but we especially encourage students and postdocs to attend that. And the links to that will be posted on Zoom, on YouTube, and on the Vamos website. So you should be able to get there one way or the other. Okay, so without further ado, it's my pleasure to introduce Ania Jayich as our speaker today. Ania is a professor at UC Santa Barbara of physics, but she did her undergraduate degree at Stanford, where she did undergraduate research with Steve Chu, before going on to do her PhD at Harvard with Bob Westervelt on imaging electron transport. And then she did her postdoc at Yale and also did some work at Harvard while she was at Yale with Jack Harris, where she did some really groundbreaking experiments, the first experiments, I believe, to observe persistent currents in normal metals. And then I had the pleasure of, when I was a grad student, working with Ania on some experiments on coupling NV centers to nanomechanics, which was a lot of fun. And Ania has really been a role model and mentor to me throughout my scientific career ever since. So it's a pleasure to introduce her today. And she's now, as I said, a professor at Santa Barbara, where she's doing really exciting experiments on nanoscale sensing, on spins coupled to mechanics, and on understanding sort of origins of decoherence and noise near surfaces. She's won many awards, including the PCASE, the NSF Career, AFOSR YIP Award, the L'Oreal Postdoctoral Fellowship. She's also currently the lead PI for the UCSB NSF Quantum Foundry and is a thrust lead on the brand new DOE QNEX Center that was just announced a couple weeks ago. Just to embarrass her a little bit, since I'm friends with Ania, I feel like I can. One thing you may not know about her was that she was at one point ranked #1 in the country in women's tennis under 18, I believe. So had things gone a little bit differently, she would have been playing at the US Open right now. But fortunately, instead of playing to an empty stadium, you have a crowd here for the AMO seminar. So take it away, Ania.
Thank you, Shimon, for the embarrassment, but also for the kind words. Just to say, Shimon is actually, I don't know who's the role model for who. But yeah, thank you, Shimon, and thank you to all of the organizers in particular for organizing this valuable seminar series in these times. I think this format is very nice, and I'm privileged to be able to participate and give a talk here today. So as I think some of you know, there'll be time for questions. We'll take a break for questions twice, but definitely I would hope to make this as interactive as possible to replicate that of a real life seminar. So it's an exciting time. Where's my... I'll just get my keyboard. Okay. It's an exciting time to be working in the field of quantum science and quantum systems today. Because of our increasing capabilities to control and utilize quantum degrees of freedom in a variety of platforms in order to gain deeper understanding of quantum mechanics, and as well as to perform useful tasks with improved performance, possibly beyond the capabilities afforded by classical elements. Here is just a small sampling of a wide variety of different platforms that we have been able to gain control of. This is, again, this is a small slice, but I picked these images just to kind of show the breadth of platforms out there, ranging from nanomechanical resonators to atomic, ionic-like systems to solid-state systems, bigger systems like superconducting qubits. And I know that many of the VAMO seminars before me have focused a lot on atomic degrees of freedom, on atomic systems, and for good reason. Atoms are canonical quantum systems. They're perfect, they're reproducible, they're well protected from their environment, so inherently quantum mechanical without really making any effort to observe quantum mechanics within them. However, reading them out on single scales and holding on to them for long periods of time is a bit challenging. There's been some amazing progress that has made that possible. So in some sense, my lab's platform of choice, which is the Nitrogen-vacancy center defect in diamond, is an attempt to realize a well-isolated atomic system, but in a platform that makes some of these challenges of holding on to defects, making them practically integrable into real-world systems right away, easier to overcome. So the NV center, as shown here, is a localized defect in the diamond lattice, specifically a nitrogen substitutional vacancy, nitrogen substitution and a nearby vacancy that interrupts this periodic repetition of carbon atoms, shown here in purple. And so this artificial atom lives in a diamond lattice rather than in a vacuum. Okay, so one might think, okay, well, it might be hard to control the quantum degrees of freedom of such a localized defect because of the presence of the lattice, but diamond actually makes a pretty good analogy to a vacuum. Why? In fact, for a solid state system, diamond is probably about as good as you can get. And why is that? Because it's stiff. That means it has a high Debye temperature of over 2000 Kelvin, which means that there's a very low population of phonons even at room temperature. Then the carbon atoms of the lattice are mostly nuclear spin free. 99% of carbon atoms have are carbon-12, which has no nuclear spin. And with more isotopic purification, which is possible, one can get even lower background nuclear spin impurities. Diamond can also be grown or formed with very few other defects, other paramagnetic impurities that could lead to decoherence. And this easily to the tune of few parts per billion. It also helps out that diamond's a wide bandgap semiconductor, and the NV defect states live deep within this bandgap, protecting these electronic states of the NV center from, say, the conduction and the valence bands. And there's been a lot of work, pioneering work, starting many years ago that sort of rest on the shoulders of, and this is obviously becoming a more and more pursued system as a quantum platform today. Okay, so as a result of these favorable properties of the diamond lattice and the nature of the NV defect within that band gap of the diamond, some stories that NV centers can have very long millisecond coherence times, even up to room temperature. Again, they have the benefit of being naturally trapped in a lattice. And it turns out that the optical transitions make it possible to easily see single spins. Somehow, okay, so part of this so what I'll just show here is that to make the analogy of the NV center to an atomic-like system, on the right shown here is a very simplified energy level diagram of the NV center, where here is the ground state electronic state, and here's the excited electronic state. In fact, the spin, that's what's missing here, but this ground electronic state actually has 3 spin levels within it, and any 2 of those can be used to form your canonical 2-level system spin system. And that's the one that has a very long coherence time. Importantly, in addition to that coherence time, as I mentioned, there's the there's an optical polarization and optical readout pathway, which allows the value of the spin state to be read out simply via the intensity of the fluorescent photons. Okay, so that kind of summarizes my plug for why we use NV centers and diamond as our model quantum system, again, sort of replicating as best we can an atomic system, but in a solid state, easy to use system. Now, more specifically, one of the things that my lab focuses on, and much of what I'll talk about today, is the fact that we use the fact that the NV is exquisitely sensitive to a wide variety of fields. It's sensitive to magnetic fields, and it's sensitive to electric fields, it's sensitive to temperature, it's sensitive to strain. And because it's so small, with atomic size, it can sense and image these fields with very high spatial resolution. And because of its high long coherence time, it can also sense these fields with very high sensitivity. As I'll discuss later on in the text, in the talk, the sensitivity is a double-edged sword though as well, right? Because if you want to use the NV center as a sensor of a variety of fields, there's target fields that you want to be sensitive to, but it also opens the NV up to being sensitive to uncontrolled fields in the environment that can fluctuate, and we have to be mindful of those. Those fluctuations can lead to decoherence, and that's something I'll also talk about later in this talk. Okay, so why do we want to, I mentioned earlier, one of the goals of the burgeoning field of quantum science is to realize technologies, in this case sensors, that might have superior properties to those of classical counterparts. So what is it about the NV center, this quantum sensor in this case, that could make it superior to some classical alternatives? And also sort of where are the fronts on which we want to push to improve the performance of a quantum sensor? So some of them are listed here. One is that quantum sensors, in this case an NV center, with its very small size, can reach very high spatial resolutions. Okay. Again, because it's atomic scale, one can really reach spatial resolutions limited to how close I can place my defect center to my target sample. Okay. And this, which can be nanometers. Okay. And we're working on techniques to make this even smaller. So the fact that we can address spins on the single spin level, and we can place them very close to the target sample, gives us this very big benefit of high spatial resolution, again, afforded by the fact that we're looking at a single spin. Okay. Quantum sensors can also have very high sensitivity. And their sensitivity is afforded, again, by long quantum coherence. One can allow a quantum sensor to accumulate phase for long periods of time where the target field is encoded in that phase. And so long coherence leads to high sensitivity. The sensitivity is also affected by the fidelity of the readout of the quantum state. The better we can read out the quantum state of the NV in our case, the higher the sensitivity. So this is a front that's also important to push on, is increasing coherence, increasing the quantum state readout, the fidelity of the readout. Another big benefit of quantum sensors, and the NV center in particular, is they're very quantitative. The field that, let's say we're trying to measure a magnetic field, the field that the NV senses imprints itself upon the phase of a quantum sensor in a very quantitative way, just related by fundamental physical constants. So this quantitativeness is extremely important and not always easy to achieve in other types of classical sensors. Another nice benefit is that the NV as a spin is a very non-invasive sensor. As a single spin itself, it's almost as non-invasive as possible. By invasive, I mean, how much does my measurement, my sensor, affect the origin of the fields under study, right? So if I'm imaging some condensed matter system, if I bring in a big, let's say I'm alternative magnetic force microscopy, I bring in a big magnetic tip to try to image local magnetic fields, the presence of my big magnetic tip that I brought in that contains millions of magnetic atoms could be quite invasive. In this case, it could affect the system under study. In this case, the NV is a single spin, can be invasive, and that actually is an interesting scenario once you get there. But in general, it's about as non-invasive as you can get. And then another sort of nice feature of the NV in particular as a quantum sensor is it's quite robust and easy to use. Again, it's robust because of its environment. Its diamond environment is a very protective environment. It protects the quantum coherence even up to room temperature, and because it's in the solid state, it's naturally trapped and quite easy to use. Okay, so with that, I will get to the outline of today's talk, where I'll focus on two general experiments. One is where we try to take advantage of the possible high spatial resolution of the NV center by building a nanoscale imaging tool, where we've incorporated a single NV center into the apex of a scanning probe tip. and made the NV center quite near the surface, quite shallow, to bring our NV close to that sample of interest. And the sample of interest can be a condensed matter sample, it can be some biological sample. I'll give you a few quick examples of some types of condensed matter systems that we've imaged in the past and focus on one particular system that we've recently been studying. And then I also wanted to spend the second half of the talk talking about quantum coherence at interfaces, which is an important issue that faces many quantum systems. The fact that the coherence of a quantum system is very sensitive to uncontrolled interfaces. In today's case, I'll talk about the interfaces as the physical surface of the diamond. But interfaces are obviously important across a wide variety of quantum technologies. If one wants to transmit or transduce quantum information from one degree of freedom to another, from a phonon to a photon, or from a spin to a photon, often that involves interfaces, and understanding the microscopic nature of decoherence and mitigating it. And what I will do is I will also show you some recent results in experiments where we have begun to not only probe the origins of decoherence, but also mitigate them by active driving protocols. Okay, so I mentioned that we're interested in the sensitivity, the NV center as a quantum sensor. So let me first just give a very quick introduction to how the spin states of the NV center are sensitive to magnetic fields, and really what's the fundamental origin of sensitivity of the NV center to fields. So I mentioned that the ground state of the ground electronic state of the NV center is it's a spin triplet. So there's 3 spin levels, the ms equals 0, plus and minus 1 of the spin triplet. At 0 applied magnetic field, it so happens that they're split by 2.87 gigahertz, which is easily addressable in the microwave domain. And because of the optical detection, because of the spin-dependent fluorescence, we can optically detect which state the spin is in, because the 0 state turns out to be brighter than the 1 state. I won't go into the details of this, but for now, let's just say the 0 state is brighter than the 1 state. Okay. At 0 magnetic field, this means that if we simultaneously apply a green laser to excite the NV center, as well as microwaves that we tune across this 3 gigahertz transition, we see a dip in the fluorescence of the NV, where the dip is located at the transition frequency between the 0 and the plus and minus 1 state. So this allows us to spectroscopically identify this transition frequency just through the fluorescence of the NV. Now, in the presence of a magnetic field, the plus and the minus 1 states, through simple Zeeman effect, will split the plus and minus 1 states by an amount, again, that's quantitative. The splitting is exactly equal to G mu times the magnitude of the magnetic field, in this case, aligned along the NV axis. Okay, so with this 5.6 megahertz per Gauss splitting, we have a very quantitative sensor of magnetic fields. And again, if we take an ODMR, optically detected magnetic resonance spectrum, we see these 2 peaks in the photoluminescence as a function of frequency that spectroscopically identify these 2 transitions, and the splitting between them is proportional to the field. Okay, so that's kind of how the NV center works as a quantum sensor. I want to stress that I've given the example here of sensitivity to magnetic fields. Turns out that electric fields and temperature also shift these levels in a way that's very distinctive. So one can separate out electric and magnetic and strain fields, for instance, by the ways they couple to the spin level. But as is shown here, just for simplicity, I've shown the magnetic field sensitivity. Also want to stress that the quantum coherence of the NV center is very important in determining its sensitivity. So in fact, the line width of these transitions tells you how well you can resolve small shifts in the magnetic field. So, so just shown here, here I've taken a zoom in of one of these peaks. In fact, you see a big splitting here, which is in fact the hyperfine splitting between the electronic spin and the local nuclear spin. That local nuclear spin also produces a magnetic field that the NV center is sensitive to. But so here, the line width of this transition here is on the order of, say, 100 kilohertz. And that line width is inversely proportional to the T2 star, the quantum coherence time of the NV center. The longer the T2, the smaller this line width, and the higher and the more sensitive the NV is to small changes in magnetic field. And the sensitivity, let's call it the DC magnetic field sensitivity, which is the minimum detectable magnetic field, say in a 1 second measurement, is given by this expression, where importantly, the T2 star plays in here. The longer the T2, again, the higher the field sensitivity. Okay, so I just wanted to stress that coherence is an important element to sensitivity. Okay, so I'm just putting the NV center as a magnetic sensor in the landscape of other magnetic sensors. Here are some that I've plotted here, starting with squids and atomic vapor cells, BECs, Hall probes, etc. On this plot, you see these various tools as plotted with sensitivity and detection volume. So to get better sensitivity means you're moving down on this plot. Better resolution means you're moving to the left on this plot. So the point of this slide is just to show you that NV centers really shine in their spatial resolution. So they're very far to the left on this plot. If you really just wanted super high sensitivity and you didn't care so much about resolution, you better use something else, like a vapor cell or maybe a very large squid, for instance. But if you're really looking for resolution, spatial resolution, combined with good sensitivity, NV centers are the type of system that are good to use. And of course, as I mentioned, additionally having these nice features of variable temperature operation and being minimally invasive. Okay, so what can one do with such a small sensor? Like, why would you want a tiny sensor? Well, one of the dreams of the field, something that our group and many other groups are sort of targeting a lot of their efforts in terms of improving the materials quality of diamond and implementing better techniques to reach high spatial resolution with high sensitivity, is moving towards really nanoscale or atomic scale magnetic resolution imaging. So currently magnetic resolution imaging is a very powerful technique that allows the detection of very small numbers of proton spins on the water and hydrogen. And for instance, taking an MRI image of your brain, one can image the proton spins with a spatial resolution of about 3 microns, corresponding to about 10 to the 12th or 10 to the 18th nuclear spins per voxel per volume pixel. So one of the dreams is can we improve the spatial resolution to be able to get down to seeing single nuclear spins and really atomic scale resolution, which could potentially lead to the imaging the structure of proteins using this quantum sensing technique. So this is, I think, not crazy, and something that one could achieve with a atomic scale sensor. Another field or subject of study is that of condensed matter systems and looking at magnetic fields arising from condensed matter systems, such as on the bottom shown here. And this is some nice results recently, where an NV center, a scanning NV center, like what what we make in our lab, has been used to image magnetic textures in this material, bismuth ferrite, where one can see the sort of cycloidal spin texture, which tells you about the local magnetic interactions within the material. And being able to see things at this length scale really tells you about the strength of the variety of interactions, which is an important goal of many condensed matter physics experiments. And as I've already mentioned, one of the goals is to get to really, for biological imaging, is get to single spin imaging of proteins. There's been some nice work along those lines using the NV center to detect single proteins and even smaller in terms of measuring nuclear spins, an amount of nuclear spins that's down to the several hundred and almost down to single nuclear spins already. And NV centers have also been used for detecting magnetic fields emanating from not just spins or magnetic textures in a condensed matter system, but also from, in this case, an interesting experiment from neurons. Firing neurons, when a neuron fires, is effectively a current that goes down the neuron that produces a magnetic field, and NV centers have been used to detect those very small picotesla scale magnetic fields as well. Okay, so in our group, and also many groups around the world, are interested in using NV centers for imaging condensed matter and biological systems. And the types of experiments one can imagine doing are looking at small magnetic textures. In this case, this is an image of skyrmions, which are these small magnetic textures that are topologically protected. I'll mention these a bit more, but there's some spin order in certain types of ferromagnets that happens on very small length scales and is an active area of research. One can also measure magnetic fields emanating from moving currents, very much like in the neuron, the action potentials. In a firing neuron, the magnetic fields are also produced by electrons that move through solid state devices. And there are interesting materials that are predicted to exhibit, for instance, hydrodynamic electron transport. This is something that I'm going to spend more time talking about. So this is going to be actually a focus of part of this talk. But just to say that magnetic fields produced by moving electrons going through solid state devices is another type of system that NVs are well suited to study, as well as the sort of goal of measuring, imaging the structure of proteins. Okay, so just a few quick words about the probes. That's one of the challenges, actually, to realizing this type of system, is making diamond scanning probes that are compatible with a variety of systems. Diamond's not an easy material to fabricate. I won't spend much time on this, but I'll just say that we, my students, are very competent at making arrays of single crystal diamond cantilevers, where each of these cantilevers has a single pillar, sort of a tip, with an NV center that resides at the apex of that tip. And so not every probe has exactly one NV center, but we have sort of a statistical probability for there to be one NV center per probe. We set the depth here to be about 20 nanometers. NVs are about 20 nanometers below the surface. Again, because of this interface-induced decoherence, that's what we've been engineering. And one of the future goals is to get these NVs even more shallow while still retaining coherence. If we take a confocal fluorescence scan of one of these probes and measure the fluorescence as we scan the laser, we see fluorescence from a single NV center in this pillar, emitting photons at the rate of about 100,000 photons per second, which is fairly bright, and thus makes it easy to see with a pretty simple confocal, almost off-the-shelf confocal microscopes. Okay, and another sort of technical challenge that we overcame a couple years ago, but just to show here what we do, is we have incorporated these diamond scanning probes into a 4 Kelvin cryostat to be able to study condensed matter systems at low temperature. Of course, one of the nice things about the NV is it operates at room temperature, but oftentimes for condensed matter systems, some of the interesting physics happens at lower temperature. And so to be able to study those systems, we've incorporated this into a 4 Kelvin closed cycle cryostat. This just shows some pictures of what it looks like. It's a tuning fork based AFM with a diamond cantilever with little, you can't really see them here, but the little pillars on the end, which we can position close to whatever sample we would like. In this case, this is just an optical image of a graphene sample with electric leads connected to it, and this big omega shaped thing is actually the RF delivery system. So this is what our cryogenic scanning NV microscope looks like, or at least a zoom in of the active area. Several years ago, we used this tool to sort of our first demonstration of extending NV magnetometry in a scanning system to cryogenic temperatures. Here just shows an image of superconducting vortices in an iron pentidiode superconductor. Again, just confirming that NV centers are compatible with at least some condensed matter systems, and being able to do these experiments at low temperature does give access to a wide range of material systems with nanoscale magnetic textures. And just one more quick example of another type of system that we've looked at, again, kind of showing the versatility of the NV center and the range of systems that we can study. Another system that we've looked at recently are these skyrmion bubbles, which, as I mentioned, are these magnetic textures, where here shows kind of a schematic of what the spins in a sample. In this case, the sample was a thin film magnetic multilayer of a ferromagnet and a material with strong spin orbit coupling. At this interface, one has the possibility of generating these spin textures, which are topologically protected, and they can be quite small. They have gained a wide, they've sort of become interesting for magnetic storage and magnetic logic, for low power devices, more in the sort of engineering sense. But one of the questions is, if one wants to use these types of skyrmion textures, one has to really understand what their local magnetic texture looks like, how are the spins arranged. And what we did is we imaged a material with many of these skyrmions. First of all, one sees that they don't all look nice and round as expected. Again, that's due to local inhomogeneities in the material. We were also able to image a single skyrmion here, and using our ability to back out the spin texture within the material, we have plotted here what the spins are actually doing, which tells you some interesting physics about what's called the helicity angle and how these spins are rotating in these structures. So this just gives you two examples of the types of systems that we've been able to probe with our NV magnetometer. And so my next thing is going to be talking about graphene and hydrodynamics, but I wanted just to take a break here for questions, kind of more on maybe the introductory part of the talk.
Okay, great. Thanks, Ania. So we've built up quite a few questions, and it's become traditional for VAMOS, as it has for many other AMO seminar series and conferences. The first question is from Bill Phillips. So while NV centers are pretty good, they're still not as perfect as atoms in vacuum. Are there important improvements in this to be expected in the future? More perfect and pure crystals, or something else?
Yeah, so I think that the main improvement for sensors, I think there's a couple of different ways that we can answer that question. If your goal is for quantum networks or for quantum communication, or photonic based applications, but here I'm going to focus my answer on for sensors, which are a little bit more robust. But for sensors, I think really, I think the main issues they're never going to be as good as atoms in a vacuum, because there is the lattice around, and it's going to be hard to remove that. But to make them as good as they can be, I think the challenge is making NV centers kind of reproducibly as good as they can be when you do have an NV center inside of a bulk diamond lattice. So when you have NV inside of a bulk diamond lattice where all it sees around is diamond, there's kind of a phonon limited coherence time, which is generally quite good, especially as one goes to lower temperatures. And being able to realize those properties, those sort of long phonon limited coherence times, even for NV centers that either reside near the surface of the diamond, which is necessary for high spatial resolution sensing or for any kind of interaction with other quantum degrees of freedom. And also not just for for NV centers residing near surfaces, but also if one wants to start looking at sort of interacting NV centers, looking at interacting spin systems within the diamond, one has to understand how to make those types of sort of dense NV ensembles without introducing more damage into the lattice and without introducing other types of defects. And so those are two, I think, two challenges to at least reach sort of phonon limited relaxation times that make the NV centers, I think, as good of a sensors as I can imagine. Maybe not atomic like, although atoms, when you bring those, if you want to get high spatial resolution with atoms, you're going to have to bring those near surfaces, and they're going to face the same problems, and their coherence times will also likely drop.
So that actually, I think, leads nicely into the next couple of questions. So from Aruku Senu and Aritra Muzumder, and they were both wondering how you make the NVs in diamond and how you can kind of control their surrounding environment and how you can control their depth. Okay, so that's that could be the topic of a whole other talk. So I'll try to be succinct here. There's many ways that NV centers are produced. They occur naturally. They can occur by implantation of nitrogen into a clean diamond lattice, and then one can also use chemical vapor deposition, CVD growth techniques, where you can dope the diamond with nitrogen during growth. And we primarily take that latter approach of we buy diamond substrates from Element 6. It's a company same as De Beers. Okay, so they provide us substrates. Then we grow thin films of very high quality isotopically pure diamond. We introduce nitrogen to the growth chamber for a very short amount of time to produce sort of very bottom up engineered gentle incorporation of nitrogen. And that ability to dope the diamond for a short amount of time and then grow a controllable amount of diamond on top of that allows us to control the depth. One can also control the depth by implantation via the energy of the implanted ions. So I guess I've talked about how you introduce the nitrogen. When you do implantation, your implantation introduces vacancies together with the nitrogen. That's unavoidable. And so you get nitrogens and you get vacancies, and then you anneal and the vacancies diffuse and they form the NV centers. In our case, we introduce the nitrogen during growth. We don't introduce vacancies during growth because it's a very gentle process. We have to introduce the vacancies. Otherwise, those can be introduced also by a variety of techniques, but we've found that the most gentle way to introduce vacancies without introducing other forms of damage is electron irradiation at very low energies, just above the threshold for creating vacancies in diamond, which is about 140 keV. And again, doing the subsequent annealing. I think that answers the depth, the formation, and there was this last part of that question. I think it's related to the rest of your talk, which was about how to kind of control the surrounding environment, which you alluded to. So I'm not going to talk a lot about, I'll talk some about that, but there's a lot of materials aspects, which I'm not going to talk about, but that's, okay. But I guess that there's more growth science, which, okay, yeah, that's. So maybe we'll do one more quick question, and then we have some other ones that we'll save for later, because I don't want to let you get on with your talk. But so Dan Stemper-Kern asks, has the accuracy of an NV magnetic sensor been tested by comparing it with a calibrated atomic vapor magnetometer or other, calibrated sensitive magnetometer? That's a good question. I have to admit, I don't know. Shimon, you probably know. I also think it's a good question. I think early on the answer is yes, but I'm not sure that it's been checked at the levels that people claim. So I think stabilities have been checked more than accuracies for NV centers. But I actually don't know. It's a good question. Yeah, and I guess I'll say for the applications that we use them for, we don't care so much about accuracy. We care about just change. We care about deltas of magnetic field produced by the sample that we're trying to image, but which is why I don't really know the answer to that question. Yeah. But yes, I agree. We'll talk about that more, Dan. Yeah. Okay, so maybe you can go on with your talk, and then we can. Yeah. Okay. Thanks. So, as I mentioned, one of our goals has been to image electron transport in material systems. Why?
because electron transport can lead, how the electrons move through a device tells you about the relevant interactions within the device. Again, that's important questions for many condensed matter systems. So here I'll just say on the right is shown a theoretical prediction of on the bottom, electrons moving through a graphene device where there's a source of electrons at the top and a drain at the bottom. And in the sort of familiar ohmic flow regime, one expects the electrons to move along these white current flow paths as shown here, if the bias is applied in this direction. But in a new regime of sort of viscous flow, in a regime where electron-electron interactions are dominant, electrons can move a bit more like honey and exhibit different types of flow patterns, as shown here in these white patterns. So I'll go a bit more into this in the next few slides. So this would be sort of an interesting demonstration of sort of a new regime of electron hydrodynamics. Okay, so electrons can move through a material in a variety of different ways. The diffusive, ohmic, and ballistic are perhaps the most commonly observed, right? In the diffusive regime, electrons predominantly scatter off of other phonons or other defects with a characteristic length scale given by LMR, where LMR is the momentum relaxation length. As the momentum relaxing, since these collisions relax the electrons, the momentum. In the ballistic regime, which is often observed at low temperatures and clean materials, electrons, there's not a lot of defects, phonons have been largely frozen out, and electrons scatter off, say, the walls of the device, off the, which has a characteristic length, this device has a characteristic length scale of W, so this ballistic regime is entered when the width, the size of the device is smaller than either the momentum relaxing length and the momentum conserving length. And again, this happens at low temperatures and clean devices. Okay, so there's another scattering mechanism, which I've referred to here, this momentum conserving, which electron-electron scattering is a momentum conserving process that preserves sort of the total momentum, doesn't relax the current. And when electron-electron scattering is the dominant source of scattering, as shown on the right here, transport can enter the so-called hydrodynamic regimes, where electrons behave more like a fluid than like independent particles in this Fermi liquid description. And this will happen when this momentum conserving, when this electron-electron interaction length is shorter than either the size of the device or the momentum relaxing. And typically it's hard to reach this regime. It's hard to reach the regime in most materials, but it's an interesting one, and it's often accompanied by novel states of matter where electron-electron interactions are dominant, and hence it's an interesting regime to pursue and probe. So the way to get to this regime is to investigate samples with long momentum relaxing lengths, so very clean samples, where you can tune the temperature to take you from, say, diffusive at high temperature through hydrodynamic down to, once you get to very low temperature, then this momentum conserving length is typically going to be longer than the length of the device as well. So at low temperatures, you'll be in the ballistic regime. But if you have a clean enough device, as you go from high temperature to low temperature, it's possible to enter this hydrodynamic regime. Okay. And there have been, this has been predicted, there have been a variety of transport experiments that have shown transport signatures that are consistent with electron hydrodynamics. And I guess just shortly to summarize these transport experiments is through these measured transport parameters, these transport experiments kind of infer what the spatial profile of the electron flow paths would look like. So these are examples of two figures. Of course, these were not directly measured, this flow profile of electrons flowing through a slit or electrons emanating from a constriction into sort of an open space. So I think it's an interesting direction to use direct imaging techniques to actually directly image this type of hydrodynamics. So we've made some initial progress in these directions. So together with Andrea Young at UCSB, who fabricates ultra clean graphene devices. We have fabricated monolayer graphene devices and used our NV sensor to image the electron flow going through constrictions with width on the order of a few microns. Okay, and here is just a current. So from our magnetic field images, as we scan the NV over this slit, the slit is shown here by these dark arrows, we can back out the current density in these devices and get a sort of a current map of the electrons flowing through these constrictions. And this work, we've also worked closely with Andy Lucas, our theoretical collaborator, who's helped with some of the simulations and the predictions. Okay, so we picked the slit geometry because the slit geometry has distinctive features for electrons in these three different transport regimes of ohmic, ballistic, and hydrodynamic. So in the ohmic regime, if one were to plot, use Andy Lucas's code to plot the current density, spatial current density, in the ohmic regime, one expects to see these what we call ears. So increases in current right near the edges of the device. One can almost think of this as like a lightning rod effect, where you have a increased electric field near these edges, and that gives you increased conductivity or current there, rather not conductivity, but current. In the ballistic regime, electrons can bounce, electrons will just bounce through this device. They don't feel each other at all, and you expect a flat profile in the current across the constriction. In the hydrodynamic regime, importantly, electrons do feel each other, and through their interactions with each other, they feel the edges of the device, and they exhibit this rounded current profile through the device. And one can achieve these different regimes of ohmic, ballistic, and hydrodynamic depending on the relative values of the electron-electron scattering length, which is this momentum conserving length, and the elastic Weaver path, the momentum relaxing length. And this is the expected for our device geometry. This is where we expect to be in the ohmic regime when electrons scatter quickly off of phonons, when electrons travel very long distances and have long electron-electron scattering, we expect ballistic. And in this interesting regime down here in hydrodynamics, when electron-electron scattering like is short, but LMR is long, we expect hydrodynamics. Okay, so as I've already showed, if we image the magnetic field through this device and back out the current flowing through the device, we get this profile. We get this image, and if we take a 1D line cut, we get this profile of the current going through the device. The black is the data, and the fit is actually a free, I don't know if it's even right to call it a fit. It's really just a free parameter model where all we've put in is the geometry of the device. And one can see that we have very nicely imaged sort of the presence of the ohmic profile at room temperature, as one would expect in a graphene device. These are, I showed you previously that one actually expects through simulation, one expects the current profile to have these very sharp features. The reason we don't see these very sharp features is because this simulation is actually convolved with the point spread function. The fact that our NV center is a few hundred nanometers away from the device. But to say that the experiment and the simulation fit each other very well. So starting at room temperature in the ohmic regime, we have done experiments where we varied the temperature, and interestingly here I show you another, I show you the room temperature data. We're at room temperature at charge neutrality, relatively low density of electrons. Again, we see ohmic behavior. As we increase the density, we see that the flow patterns change a little bit, but overall still looks, we have the presence of these ears. We see that the flow is ohmic, maybe a little bit less ohmic, as one might expect actually. But importantly, as we go to low temperature at 128 Kelvin, where we've now increased the momentum, the LMR, the momentum relaxing length, to the point where the electron-electron scattering length can drop below that of the momentum relaxing length, we see that away from charge neutrality, we see these profiles that are consistent with non-ohmic flow. So we've seen a transition from ohmic flow to non-ohmic flow as we go to lower temperature and away from charge neutrality. At charge neutrality, you still expect ohmic flow at low temperature because there's a fair amount of scattering, there's electron-hole recombination, not a lot of screening there. But. Okay, and quantitatively, we've analyzed these data sets to extract what's our best fit for the momentum relaxing and the electron-electron scattering length at these different temperatures and these different densities. And what we see here is that 128 Kelvin and away from, I'm not showing the charge neutrality here because it's ohmic and we expect it to be ohmic, but away from charge neutrality for these finite densities, the data is consistent with collision-dominated electron flow, this regime where the electron scattering length is small and is dominant. I'd say that this complements the nice recently published work out of Shahal Alani's group, where they used a different type of detector, not an NV center, but scanning SET to image the transition from the lower temperature of the thing, from the ballistic to the non-ballistic side of things. And so, anyways, this is sort of the results of that work. Okay, so in the last few minutes, I will quickly go through quantum coherence at interfaces. So, and I'll go through this a bit quickly because I think a lot of these are probably fairly well understood. It's important for, if we want to have really high spatial resolution, really high sensitivity, we want to bring our NV center as close as possible to our target system as possible. That means that we want this distance r to be small. Because our dipole sensitivity gets much smaller, we want sort of small sensitivity. Sensitivity to few numbers of Bohr magnetons will go as r cubed over e to the minus t over t2. So the challenge is we want to make r small and we want to make the t2 long. However, that's a hard challenge because generally as you bring an NV center close to a surface, as you make r small, this t2 time gets smaller. Why is that? There's a variety of reasons. They're not all totally clear, but surface is basically uncontrolled. The diamond has this nice pristine diamond lattice. It's very protective of the quantum coherence, but the surface is uncontrolled. There can be trapped charges and trapped spins. There could be strain fluctuation. There can be dangling bonds, and those can reduce the coherence. And this surface-induced decoherence, I'd say, is a universal nuisance. It's a major roadblock to a variety of developing quantum technologies shown here. If you want to bring trapped ions close to surfaces, they suffer from surface effects. Superconducting qubits suffer greatly from interface-induced decoherence. Even nanomechanical resonators, their quality factors are limited by small numbers of defects arising at the surface. For NV centers in particular, we've seen that the quantum coherence time of an NV center drops dramatically once you bring the NV center within about 20-30 nanometers of the surface. So this just plots T2 as a function of depth. And again, things sort of are bulk around 20-30 nanometers, but drop when they get near the surface. In addition to quantum coherence dropping, charge state stabilities of these defect centers also tends to get worse near surfaces. It's just yet another problem with interfaces and surfaces. I think I will skip these two slides because I want to get to I think an interesting point. So it turns out that we've identified that surface spins, and there's been a few people working on this, where surface spins are indeed one of the sources of decoherence at the surface, the presence of these paramagnetic spins. Interestingly, though, we are able to detect the dynamics of these surface spins, and we see that their surface spin spectrum is actually quite narrow. So in fact, these surface spins have reasonable coherence times. In fact, we can even drive Rabi oscillations of these surface spins. So this is a plot showing using the NV center as purely an optical readout here, that's dipolar coupled to these surface spins, we can drive these surface spins and measure Rabi oscillations of these surface spins using what's called double electron resonance techniques. I won't get into the details of how we do this, but again, the main point is we can address these otherwise dark surface spins, which are hard to detect on their own, but using the NV center, we can address them. They're relatively coherent. We can drive Rabi oscillations in them. Not sure if this is the best time to break for questions. I think given time, let me just get through these last few slides, and then those questions I think will come up, because I only have a few more slides here. Okay, so how does one mitigate decoherence of quantum systems? Okay, one can take a materials-based approach, sort of what Bill Phillips was asking. How do we clean up the material, make it more pristine, clean up the surface? There's ways to do that. You can etch the surface. You can terminate the surface. Those are good approaches, but not always super long term, right? If you're using your NV center in some environment over time, the surface is going to get gunked up. Okay, so that's not always the best solution. One can exhibit quantum control of the qubit. This is typical. We all do this for our quantum systems. We exhibit quantum control. We apply dynamical decoupling sequence to the NV center. These are powerful. These can extend the coherence of the NV center, but they're also sort of time intensive and they use a lot of bandwidth of the NV. What about directly controlling the environment in situ? What about taking this offending environment and just addressing that part of the environment? So this is kind of the schematic shown here. We have a qubit, we have this decohering environment. If we can apply a drive to the environment, we can control our qubit with our regular sensing sequences, gate operations, whatever we want to do, but simultaneously drive the environment in such a way as to mitigate its decohering effect on the NV center. That's a powerful approach. And so there, with one can imagine if you're driving the bath, you can increase the coherence of the NV center of a spin. It doesn't have to be an NV center. And this relies on the important fact that not all fluctuations in the environment produce decoherence. We normally think of decoherence as interactions with the environment, entanglement with the environment, uncontrolled fluctuations in the environment, but not all fluctuations produce decoherence. Only certain frequency components in the environment contribute. So for instance, if you apply a Hahn echo sequence or some dynamical decoupling sequence, you're not sensitive to low frequency fluctuations in the environment. And if the environment is fluctuating at very high frequencies, those effectively get time averaged away in analogy to sort of motional averaging in NMR. And this can be seen as the T2, the coherence time of a qubit's given by sort of the inverse of this integral of the noise spectral density and whatever frequency filter you apply to your qubit. And so typical dynamical decoupling, what it does is it just shifts your filter function. In this case for a Hahn echo, it shifts your filter function of your qubit far out of the spectrum of the noise. And so then your signal, you also need to make sure that your signal is also correspondingly moved to this frequency of the NV filter function. But another approach, if you were to drive the environment, let's say you have a signal that's sort of overlapped with your fluctuating environment, it's hard to separate those out. If one can drive the environment in such a way as to actually move the environmental spectrum out of the frequency of the signal and keep your filter function here, which seems to have disappeared, that's another approach to mitigating, or there's a decoherence. So we've taken two approaches recently to realizing this driving. One is monochromatic driving, where we drive the environment with a single tone drive. What that does, as I just showed, is it basically takes the spectrum of the noise and shifts it by an amount given by actually the Rabi frequency of the drive, and separates the noise in the spectrum of the noise from the filter function, from the frequency of fluctuations that my NV center is sensitive to. Now one can apply an incoherent drive, so a drive with many frequency components. And by doing that, one does something very different. One actually reduces the correlation time of your environment. That's what I've shown here. So if the gray thing is the magnetic field as a function of time, before applying a drive, it maybe had a correlation time of tau c. But now if I apply an incoherent drive, I'm reducing the correlation time of my environment. When I do that, I effectively flatten the power spectrum, okay, as opposed to shifting it in this case. I flatten the power spectrum. And again, the overlap of my filter function and my power spectrum is now reduced in a different way. Okay, so I think I already said why these types of driving the environment approaches are nice. So I guess I'll just show you that we've done monochromatic driving. We've driven the surface spins. We've increased the quantum coherence of our NV center. So here shows a Hahn-Echo coherence decay with driving, without driving. And that increases our sensitivity by about 5 times. We've also recently done incoherent surface driving, where we've driven the surface spins with a drive that has a bandwidth that's broader than the width of the surface spins. These just show the Rabi oscillations of the surface spins, and this is just showing that as we increase the bandwidth of our drive, we're actually dampening the surface spin Rabi oscillations. We're reducing the correlation time of the surface spins. And if we look at the T2 of the NV center with this incoherent drive, as opposed to no drive on, we see that the coherence time increases up to a factor of 3. That's what's plotted in yellow. We can also increase the coherence time with this coherent drive, as I mentioned, this monochromatic drive. We also see this increase in coherence, but what we've shown is this incoherent, this broadband drive is in fact much more effective and efficient at decoupling, at reducing the decoherence from the fluctuations in the surface spins. And this just shows that we can, this is just the T2 of the NV as a function of the broadening of our drive. So there's some sort of optimal broadening. Okay, so 1 minute over, I guess, just in summary, I've hoped I've shown that the NV center is a versatile quantum probe that yields insight into magnetic and electronic properties of condensed matter systems. I showed you briefly some skyrmions and talked about imaging electron flow patterns in graphene. And then I've also discussed decoherence interfaces being a major challenge to many technologies. NV centers are actually good at illuminating those noise origins. I didn't talk so much about that, but I did talk about the fact that we've been able to use the NV center to demonstrate how novel environmental driving approaches are a powerful way to extend the coherence of NV centers in a very sort of robust and in a way that leaves the NV center or the qubit free to do whatever gate operations can be done. So with that, thank you very much.
Okay, thanks for a great talk, Ania, and I think you're right on time. We took some questions in the middle as well. So, so there's a lot of questions that have built up. I think we won't be able to get to all of them, so I'll remind everyone that there will be the opportunity to chat with Ania after this in the discussion session. We can go ahead and do some now. So KB Ing asked, are those electron spins on the surface unpaired electrons from contaminants or NV-like centers on the surface or near the surface?
Good question. I think the origin of those is not totally well understood. There's some work, surface studies, in particular Natalie De Leon at Princeton, along with a few others, have done some work showing that they could potentially be sp2 diamonds or dangling bonds. I think the jury's still out. I think there's these surface spins, I will say, are very interesting to us. Not only their decohering effects, but the fact that they are coherent, and the fact that we could eventually gain control over these for very useful purposes. I think it's pretty amazing that you can have spins at room temperature in air on the surface of something that have sort of almost microsecond scale coherence. And, we work so hard to make superconducting qubits coherent at, dilution refrigerator temperatures, and here we have some junk sitting on the surface. Okay, so I guess just to say that I think these are very interesting systems, and their origin, and which is why we're interested in understanding what they are. I think the short story is it's unclear. They could be sort of sp2 diamond dangling bonds, possibly.
Okay, so then we have a question from Dima Budker. He says, thanks for the great talk, Ania. Could you kindly comment on the relative efficiency of the dynamical decoupling sequences in mitigating electric versus magnetic noise-induced decoherence?
So okay, so how good is dynamical decoupling at decoupling electric field noise from magnetic field noise? I mean, I think that's a bit of a complicated answer because I think it depends, first of all, how affected you are by electric field noise or how affected you are by magnetic field noise to begin with depends very sensitively on what magnetic field you're working at, what transition, if you're looking at the 0 to 1 transition or the -1 to +1 transition, what's sometimes called a double quantum transition. And it depends on the spectrum of the magnetic field noise and the electric field noise, which will vary significantly depending on if you're near a surface or you're away from a surface. So I don't know if I can give a sort of broad answer that gives one answer to that. I guess I would say, if I were to give one, I guess if, maybe just one thing is we've been able to discriminate sources of electric field induced decoherence and magnetic field decoherence using, again, this is near surface NV centers under the surfaces that we've prepared. So we're able to largely decouple electric field if our dynamical decoupling is fast enough to decouple up to 100 kilohertz, because electric field noise seems to contribute strongly at low frequency. So in this specific example of NV centers near a surface, about 10 nanometers or so below the surface, we're able to decouple most of the effects of electric field, but not all the effects of the magnetic field.
Okay, thanks. So Gabriel Moreau asks, are there prospects for improving the precision of NV centers to match that of squids? Or is the precision resolution relationship really a hard trade-off?
The precision of squids. Sorry, is it a hard trade-off between precision and spatial resolution?
Yeah.
I mean, there is a hard trade-off, certainly for squids. As you make them bigger, their sensitivity increases and their spatial resolution decreases. So that's, I think certainly for squids, there's definitely a trade-off there. I think for NV centers, that trade-off maybe doesn't exist so much because you have a single NV center, so you can't really make it smaller or bigger. I think the current sensitivity of squid, and again, comparing, say, a single NV center to a squid that's maybe 20, that's maybe comparable to sort of state-of-the-art squids that are these nano squids that are maybe 20, 30 nanometers in diameter. Those are currently equal. I'd say one can improve. And I think there's a lot of room to improve NV centers, in particular in this high spatial resolution limit, by addressing these surface-induced decoherence and using some of these techniques that I've talked about. So I think that's definitely an approach. I think on the squid side of things, of course, if they continue to make things smaller, they can get higher spatial resolution. I think, it's just in comparing to squids, my main comparison that I think of is that NV centers offer higher spatial resolution. I think in terms of sensitivity, pure sensitivity numbers at this point, squids, I think if I had the choice, squids would be superior. But if you're really trying to get high spatial resolution, targeting sort of nanometer scale spatial resolution, I don't see that happening anytime with squids. And that's the kind of problems that I think it's useful to use NV centers for, and the wide sort of temperature range as well. So.
Okay, so we had actually a couple of questions that wanted to know about the timescales for these kind of measurements. I think especially your scanning experiments in the first part. So there was a question of how long does it take to image, say, vortices and superconductors, and can you see dynamics with these techniques?
Yeah, so I'd say the images that I've shown, typical timescales there. And by the way, this reminds me, I didn't show my last slide because I wanted to bring up one of the students here. So Alec Jenkins, who's actually a postdoc now with Adam Kaufman, he can answer this question much better and sort of to his pain, but those images could take several hours. some of the improvements that we're trying to make are obviously aimed at reducing the timescale of those imaging experiments. So yeah, I'd say sort of on the order of several hours, depending on the strength of the signal, obviously the sensitivity, the resolution, the magnetic field resolution that you're trying to attain. Was that was the main question, right? Did I?
Mm-hmm.
Okay.
I think so. And then maybe a related question was from Natalie DeLeon about the hydrodynamics measurements. So
yes.
She was wondering what's actually limiting how close you can get to the device. You mentioned that you were limited at sort of 100 nanometer scale.
Yeah, there are some technical issues that we don't actually totally understand. I mean, for one, there in that particular device, we had a layer of HBN on top of the graphene. So that gave sort of a limit of about, I think, I forget if it was 20, 30 nanometers or so, but small compared to the 100 nanometer scale separation. So part of that is the tilt of our cantilevers with respect to the sample. So if there's a little bit of a tilt, then if the NV center is not at the very, very, one end of the probe, it's going to be removed from the surface. And then we suspect that oftentimes actually it's just cleanliness of the sample and of the imaging environment, because we tend to pick things up on the tip, and those little pieces of junk on the tip tend to make us further away from the surface. And so that's, again, it's a bit of a technical issue of how do we clean the samples and how do we image very gently so as not to pick things up on the tip. We've had other experiments, I should say, that we've gotten down to 15 nanometer separation between the NV center and the sample under study. But it tends to vary from experiment to experiment, and presumably due to tilt, picking junk up, technical issues that continue to be resolved. And before I finish the next, I just wanted to the slide is important, and I didn't show it. I usually show it at the beginning of my talk, but this is why I do that. I just wanted to thank all the students, of course, who did the experiments, primarily Maxime, who did the incoherent driving, really inspired by Dolev Blevstein, an undergraduate who's now in Misha Lukin's group, who's really spearheaded the sort of environmental driving experiments. Alec, who's done a lot of the scanning experiments, together with Simon here, and Suzanne was also a postdoc who was involved in the scanning experiments as well. So, and these are all the collaborators that we've benefited from working with. So I apologize, and our funding agents, I got too excited and didn't show the slide.
So maybe we'll actually stop there. We have actually a lot of other excellent questions, and I'll just encourage everyone who still has a question. I'm sorry I didn't get to it. To chat with Ania and ask those questions during the discussion session. But let's thank Ania again for a really great talk. And then I'm going to take over and hijack the screen from you, Ania, so that I can show this slide. So next week, there's a couple of really exciting, great talks. So our sister seminar in Europe, the Quantum Science Seminar, we'll have Pete Schmidt from PTB and Leibniz University talking about quantum logic spectroscopy of trapped ions on Thursday. And then we, next week on Friday, we'll have Letitia Terrell of ICFO talking about engineering chiral solitons and density-dependent gauge fields in Raman-coupled Bose-Einstein condensates. And that'll be at the usual time. So I encourage you to attend both of those seminars, but even more, I encourage you to attend the post-seminar discussion, which should be starting now. And again, we'll be posting links to that in the chat. There we go. Thank you, Christy. Christy just posted a link along with the password to enter. The way we're going to be doing it from now on is using the same link every week, but changing the password so that we don't have potential issues with Zoom bombing. You have to sit through the whole talk in order to figure out how to get in there. So and so we'll see you there, Ania, and hope to see a lot of you there as well. Thanks.